In the previous session, we talked about big O notation, time complexity and space complexity. Now it's time to talk about the data structures. Again, if an algorithm is basically the problem that you want to solve, then the data structures are the tools that we can use to solve that program. And the first one is an array and a vector. So let's just get into our code right over here. I have prepared here a simple array and a vector. Now, what is the difference between an array and a vector? But even before we jump into that, because there's a significant difference between those two. Let's just talk about what an array actually is. It's a collection of elements of the same type. So it's not a tuple. You might be familiar with tuples. It's of the same type. As you can see, currently it's I32, the default one, and this array has 7 elements. So this is the first one, 7, second one, 3, third one, 5, and so on. Now, the good thing about arrays is that they are contiguous. So what that means is that, let's say, our compiler needs to store this on our memory. It searches for a slot where all of these 7 elements can be allocated, and that's it. We have our array. Now, if we do want to add a new element, let's say at the end of this array, like a push or append to this array, then our compiler would need to take this array, put another one, another new element at the end, search for a new memory compartment with all of the available slots so we can store the array plus an extra element and then put it in there. Now, an array, in other languages, it might be called a static array, meaning that it has its element constant. So it has a cap. This one has 7 elements, as you can see. And the difference between an array and a vector is that the vector does not have this strict feature, like it's the same, these are the same elements, as you can see, but the actual memory allocated to this vector is actually double, like 14 in our case. What that means is right over here, after the last elements, think of it like we still have 7 new open memory slots available. And that's really great because if we want to add, append, or push a new element to the vector, then we don't have to do the whole copy thing and searching for a new memory place. We just insert that element at that particular index, which is O of 1. It's constant. Now, if we fill up all of the 7 available reserved memory slots, and we still want to add a new one, then that O of n time complexity will happen, because now we are going to copy out all of the 14 elements, find a memory slot that has actually 28 available memory slots, and then paste in, just put in all of the 14 elements, and another 14 are reserved for future use. That's what our vectors are under the hood inside the memory. So therefore, an array and a vector has different time complexities in just a few cases, but it's notable. Let's take a look at how we are accessing. And before we go into accessing, how do we access? This is because it's a contiguous, so it's in memory, it's one after the other, in memory slots. Therefore, it's really easy to just go to the next memory slot, and find that element. And we are storing that as indices. So this is at index 0, 1, 2. We're not starting indices from 1. In computer programming, we are having it as 0. So 0 index is at the first element, 1 is the second, and so on. So that's how we access. Basically, we just say array and at a particular index, and that is O of 1. So constant time. It's instant, right? So if we, lookup is instant. That's the whole one of the most important powers of an array. Same goes for vectors. Now updating, same thing. O of big O of 1. Because again, we are accessing the element that we want to update at that particular index, and we just swap it instant. Inserting at the beginning. Now this is actually O of n. Why is that? Well, first of all, let's talk about the array. So if we want to index insert an element right over here at the very beginning, what that will do is actually we still have to find a new place for our new array because it has a new capacity. It's 8 now, and we're going to store all of this in a new array 9, 7, 3, 5, and that is O of n. We need to go through all of our array. Now, inserting in the middle doesn't really change anything. Let me just put it over there, O of n, because of time complexity is how we are, measuring time complexity. If we are dividing by a constant, it's still O of n. So it will take up linear time. Inserting at the end. Now, this is where kind of the trick is. If you want to insert right over here, that 9 at the end, well, we still have to do a new array, still have to allocate that that memory. We have to find it, we have to put it. So on the array, it's still O of n. But on the vector, if you want to add a 9 right over here, remember that memory slot is reserved. So it's over there. So it's O of n. So we can just put it big O of 1. It's constant because now we just need to just add it. Now, it's not really constant because what happens if all of my reserved memory slots are going to be populated? All of the 14 elements are done. Then on the 15th one, we still have to do the thing that we did with the array. That will also be O of n. So actually, this is amortized. So you, in general, like on the sum of it, because when you are having 14 and we want to add in the 15th, we're still, we're going to take up O of n, O of n on the, like we did with the array, but the vector will double in size again. So we have all of those reserved memory slots. Therefore, inserting at the end again becomes O of 1. So all in all, amortized, it will become O of 1. Removing at the beginning, so that will be O of n again. So O of n, because let's just say we want to remove the 7, we still have to, and again, these have to be mutable. We're going to get into the syntax when we are going to take a look at the project, the actual problems. But removing means that we have to shift each and every element by 1 to the previous one, to the previous one, to the previous one. And that takes up O of n time because we are going through all of the elements inside an array and also inside the vector. Removing from the middle, same thing, because it doesn't really matter if we just start from the beginning of our vector or at the beginning, at the middle, or rather, near the middle or near the end. It's still O of n because we are dividing by a constant. Removing from the end, it's interesting because that is O of 1. It's just the last element. It's simple, really great. Copying, you already saw that it's O of n because we need to move through each and every element inside our array /vector.